Alright, welcome back. Hey, if we're going to be talking about parts of the climate system that we might be able to numerically model and understand over and above what we already understand with regard to like the changes in the atmosphere, how about the cryosphere? I mean, the cryosphere is primarily physics. It's melting ice, it's changing albedo, it's gravity moving the position of a glacier, and so on. We should be able to make physical models of, numerical models of what the cryosphere is doing, and again, it's going to have to be some kind of coupled model. We're going to have some kind of numerical modeling of the cryosphere, which is a thing, okay? There are busy little grad students out there at various schools right now, running simulations of what this ice sheet is going to do, or what this layer of permafrost is going to do, or whatever. It's a thing. It exists. You can read papers about it. They sound boring, but you can do it. And you can kind of envision how, again, it would have to work. There'd have to be some kind of equations that describe the physics of what's going on in the cryosphere. We'd have to have ways to estimate things like changes in the thickness and areal extent of sea ice, or how a glacier will move as it travels down a slope of this valley, or whatever. And we could have to have that somehow coupled to what's going on in the atmosphere, so that we could say, as these temperature changes happen, or these precipitation changes, or these cloud cover changes happen, how is that changing what's going on in the cryosphere? And, actually, ideally, it should be a two-way interaction, whereas changes in the cryosphere happen, they could change what's going on in the atmosphere. Like, if you had more extent of sea ice, or if you had less extent of sea ice, or whatever. You could be changing the fluxes of heat and moisture out of the ocean into the atmosphere. Oh man, it sounds like a whole nightmare of another type of numerical model. And that's exactly what it is. I mean, I don't know if it's so much a nightmare. I guess it's probably a nightmare, but whatever. What do you think the IPCC has to say about all that? Well, in the fifth assessment report, they say that most of the CMIP-5 models, by the way, CMIP is the Coupled Model Intercomparison Project, version 5. Notice the word coupled in there. Most of the CMIP-5 models predict a nearly ice-free Arctic. In other words, this is how they defined it here. By the end of the summer of 2100 in the RCP 8.5 simulation. 2100 is pretty far into the future. RCP 8.5 is a pretty warm simulation. That with the very large 8 watt per square meter, 8.5 watt per square meter anthropogenic forcing. And we know that a realistic range for anthropogenic radiative forcing is going to be somewhere around 4 to 8 watts per square meter. So it's on the high end. Okay, that sounds scary, but that's pretty far in the future. Maybe oh, wait a minute. By scaling some of the CMIP-3 models with recent observed sea surface September ice changes, okay, I don't quite know exactly what that means, and we could read the context in the paper. A nearly ice-free Arctic in September is projected to occur by 2037, reaching the first quartile of the distribution for timing of September ice by 2028. In other words, 25% of the simulations are saying that by 2028, we're going to start seeing ice-free summers, with most of them showing by 2037. You guys are young. I think you're going to be there in 2028. I think I'm going to be there in 2028. Wait, I'm not that old. I better see 2037. I better see a little bit later than all of these things. I don't think I like the idea of an ice-free Arctic. Again, this is kind of a probabilistic thing here, because, they're saying some models are showing it by this time. But this looks bad, especially in light of, remember, we saw some observations of like sea ice coverage in recent years and how bad the sea ice coverage has gotten in the recent winters. Oh, in light of all of these results and others discussed in further detail in the IPCC report, it is very likely that Arctic sea ice cover will continue to shrink and thin year-round during the 21st century as global mean surface temperature rises. It is also likely that the Arctic Ocean will become nearly ice-free before the middle of the 21st century in the higher greenhouse gas emission scenarios. So far, we are very much on those high scenarios, so that looks really bad. Well, that's great. keep in mind, words like very likely are defined. I mean, they're like, what, 99 to 100% chance or something like that. I think that's actually nearly certain. You'd have to look at the footnotes as to what exactly very likely means. But it's a high probability of, of these results being correct. Oh, I don't like that. I don't like the thought that there could be all these big changes happening in the sea ice distribution, especially in the Arctic. The atmospheric scientist in me thrills and fears the changes in the fluxes of sensible heat and latent heat that will be changing as the sea ice extent gets thinner and thinner and covers less area and so on. But there's other really bad and scary things going on in the cryosphere too. Other cryospheric changes, for example, could be happening to permafrost. Now, odds are you don't think about permafrost very much. I don't think about permafrost very much. We should all think about permafrost a whole lot more. If you're unfamiliar with permafrost, just to pull a dictionary definition out of the glossary of meteorology here, is a layer of soil or bedrock at a variable depth beneath the surface of the earth in which the temperature has been below freezing continuously from few to several thousand years. These are places where the soil is frozen year-round to some great depth. Often near the surface, the highest maybe meter or so, there'll be an annual thaw in the permafrost. And you get like shallow roots, and, grasses, shrubs, dwarf trees, things like that. This is the kind of environment that we call a tundra, for example. But below that, it's ice. And I don't mean like it's an ice sheet. This picture here is actually a little bit misleading here. I wonder if I have a better one on the next page here. I don't. Picture more like frozen soil. It is a matrix of dirt and ice. This seems awfully icy over here, okay? It's organic matter, as all soil is, but whatever's organic in it, it's locked in there because it's frozen. Okay, there is not a lot of bacterial activity, there's not a lot of worm activity, there's not much going on in it. It's frozen. Okay? Now, unsurprisingly, the models in general are going to be showing a decrease in the amount of permafrost because, especially in the Arctic, where most permafrost is, we are going to have warming temperatures. Which you might think, oh, that's a problem for ice road truckers and those Discovery Channel shows where they're digging for gold in Canada and stuff like that, but surely this doesn't matter to anybody else, except it is a very big problem, because permafrost is one of the world's great big reservoirs of carbon. See this permafrost here? I don't remember if this is a mine or where exactly this is here. See all this soil? See how there's kind of a layer of soil that's probably thaws out in the summer, and there's like, living roots and things in there. And then to greater depth, it's a matrix of soil and ice and so on. And there's stuff in there. Dead roots, dead sticks, partially decomposed leaves, all kinds of organic matter that was trapped in there as it froze. Guess what? That's a reservoir of carbon. It's sequestered in there. And we're not talking a small amount. The aerial extent of permafrost is pretty impressive. I mean, take a look at a globe sometime. Look at the North Pole end of it, and look at it like, northern Canada, northern Alaska, and Siberia, and Scandinavia. There's a lot of permafrost in the northern hemisphere, and together it stores about 1,670 petagrams of carbon. Petagrams? A petagram is actually a terrible unit of carbon, but it can be converted into a gigaton. A petagram is a gigaton. Alright, well, from our studies earlier where we were talking about the carbon cycle, you might remember that anthropogenic sources of carbon, like burning of fossil fuels mainly, releases about 10 gigatons of carbon into the atmosphere a year. And there's 1,670 gigatons of carbon stored in the tundra, which is not so great. So basically, the amount of carbon that is sequestered in the tundra is equivalent to several hundred years of anthropogenic emissions. Okay? Wait a minute, and that's not that stably there. See, as the permafrost thaws, bacteria in the soil start being able to consume the organic matter, partially decomposed leaves, peat, roots, whatever it was. And by the respiration of that bacteria, they return the carbon back to the atmosphere. It's a transfer of carbon from the land biosphere into the atmosphere just because we let things start to defrost. And as we defrosted them, we are introducing more carbon into the atmosphere. Oh, this is great. This is great. We've just now added another way that something we're doing is putting carbon dioxide back in the atmosphere. Great. It's another stupid feedback. Does that mean that it's going to happen? What's going to happen to all that permafrost? Well, at least to some depth, it's going to melt. Okay? A warming planet, it will... It's a good question as to how deep it'll melt, but to some depth, it will melt. And there's nothing we can do about the fact that bacteria and other living things are going to get in there, and they're going to consume that organic matter and convert it back into carbon dioxide, which will only end up back in the atmosphere. And these changes are irreversible on the scale of thousands of years, right? It isn't like we can somehow, I don't know, grow some material, grow a bamboo forest in Alaska, and then, you know, to pull carbon out of the atmosphere into the wood of the bamboo, and then bury it under ice and make new permafrost, right? It's irreversible on the scale of like millennia at least. But here's the funny thing about it is there's just wild uncertainty as to the rates at which this will happen, the rate at which the thawing will happen, the rates at which when the thawing happens we get the biologic activity to change the carbon back that's stored in the organic matter back into the atmosphere. The models that we have of this kind of thing are producing wildly different answers. So at the present time, we don't actually have some kind of coherent result as to how much of a feedback this is. Is this something that changes everything really fast? Is this a slow feedback that takes thousands of years? We just don't know under any kind of plausible future warming scenario. I included on here the verbiage that what this really tells us is how little we actually understand what's going on in soil. Consider this a plug for an Earth System Science class. You might know that there's some reason to be optimistic that a Earth System Science class may be added to the environmental science curriculum sometime soon, and I think it's great. And if you don't get a chance to take one while you're in Creighton, make sure you find some time in your life, you know, in grad school or something to take them, because that's an important thing. Alright, this has all been near-term stuff. Oh, I'm not looking forward to seeing that. Oh, stop the world. I'm tired of being here. I'm old. I don't want to see these kind of changes. I don't... well, guess what? That's called life. We all have to. We all live to see the world we didn't think we were going to see, right? Next time, we're going to talk about more distant changes. What could happen in the coming centuries? In the meantime, though, let's answer two more quick questions. Question 7. While it's true that we expect the sea ice coverage of the Arctic Ocean to decrease between now and the middle of the 21st century, climate models suggest that there is no reason to think that the Arctic Ocean will ever be completely ice-free in our lifetime. True or false? Make a choice from those two options and get a little feedback before you move on to our final question.